Okay, so let's start. Welcome to this course on convex optimization. So before we actually begin the course, let's go over some basic administrative stuff. So first, the prerequisites. I will assume a strong foundation in linear algebra and matrix theory. That's going to be fundamental to this entire course. And is there anyone who has not taken a linear algebra or matrix theory course? You've taken a linear algebra course? Yeah, that's fine. One of those two courses is enough. And just to get a sense of what was covered in these courses, what was some of the final topics that were covered in your linear algebra or matrix theory courses? Eigenvalues, eigenvectors, hopefully all of these were covered. Did you cover anything related to positive semi-definite or positive definite matrices? How many of you have not heard of positive semi-definite or positive definite matrices? It's okay if you haven't, I just want to know. Okay. Singular value decomposition. Okay, so SVD was hopefully covered in the course. Were any results related to symmetric matrices covered in your courses? Okay, fine. But at least you know, for example, what the column space is. How do you solve a system of linear equations? What is a determinant? What are eigenvalues and eigenvectors? So it's a good idea to refresh your basics from matrix theory or linear algebra, as we'll be using them extensively. So I will do a very quick review of some of the basic concepts in this course, but it will be very short. So you should really go through, revise your notes or textbook, whichever you used for the linear algebra or matrix theory course. Right? And we'll also be using a fair amount of multivariable calculus. Again, we'll very quickly go over some of the basics, whatever is required for this particular course. But since after all this is a course on optimization, I will not have time to go over proofs or too much in detail. All right. Okay. It's good if you have taken a course on probability and random processes, although it's not essential. I'll mainly be using it for some examples during the course. Right? But what will be necessary is some comfort with programming. We will be doing a fair bit of programming and there will be programming assignments. It's good if you already know some Python programming, but the language is not so important. You can pick it up as we go along. But certainly comfort with programming is a must. Right? And the assessment, again, I'll finalize this maybe in a week or so, depending on how many students we have in the course. But essentially, a large chunk of the evaluation will be based on exams. There'll be around 3-4 exams spread across the semester. But in addition, there'll also be in-class quizzes. So I'll give a number of assignments, but these assignments don't have to be handed in. But you can certainly expect many questions from the assignments to appear in the exams, right? So you should really go over those theory assignments. And in-class quizzes will mainly be like very short quizzes, 5-10 minute quizzes in class, where I'll just want to check that you're following what is going on in the course, right? These in-class quizzes may not be announced beforehand. These will be surprise quizzes. But the exams, I will announce them, and most of the exams will be during class hours. 1 or 2 may have to be like off hours. There will also be some programming assignments, and I'll give you more details about that. In case you want to discuss something about the course with me off class hours, You can just email me, set up an appointment. My office is EE616 in the electrical engineering building. And we'll be following this particular slot since we have a number of students from diverse backgrounds and different branches. Scheduling will always be an issue, so we'll probably stick to slot R. So this will be Tuesdays 2:30 to 4 and Fridays 4 to 5:30, and classes will be conducted here. Okay. References and other material will also be shared in this course webpage. So for the first few lectures, I won't follow any fixed reference. I'll point you to material and you can see the lecture notes. But for a large part of this course, I'll follow this book by Stephen Boyd and Levin Vandenberg. It's called Convex Optimization. There are a number of libraries, number of copies available in the campus library, but you can also get a soft copy available for free from the website. A link is also provided in this course webpage, right? But there are, I'll add some more references, but just to begin with, this reference is particularly nice. It's by Chong and Zach, and it's called An Introduction to Optimization. I think a few copies of this book are also available in the library. It starts off in a very gentle manner. It covers a lot of the prerequisites in a nice way, and a good chunk of it is dedicated to single variable optimization. So we'll graduate beyond that and go to Boyd and Vandenberg pretty quickly. But this is a nice place to develop intuition and just get started with the basics of optimization. The third reference is a more advanced book. It's called Algorithms for Convex Optimization and covers a lot of the latest algorithms that have been developed for optimization itself. Right. I'll let you know which sections and which references to go through as and when we cover those particular topics. All right. And as I said, I'll need a background in Python programming. Effectively, we'll be using just 2 or 3 basic libraries. If you programmed using NumPy and Matplotlib, that should be more than enough. But if not, there's a very basic set of lectures on Python programming here. I'll also maybe add a couple of references for NumPy and Matplotlib. We won't require anything too advanced. We'll also be using another library called CVXPy, but I'll introduce that during this particular course. All right. And for the basics, here are some references for linear algebra and basic analysis. And if there's any other material like list of topics, corresponding references, lecture notes, all of this will be uploaded to this course webpage. All right, so keep looking at the course webpage on a regular basis. All of this will be here, and assignment submissions and announcements will be on Google Classroom. So in case you've just registered and have not got an invite for Google Classroom, just wait for a couple of days. In case you still haven't got an invite, just send me an email. All right. Yeah, just go over this course webpage completely. Any questions related to logistics? Yeah. I'll wait for at least 5 minutes every class. But yeah, so 5 minutes should be perfectly fine. Any other questions? Okay, so maybe let's just begin. Let's just have a quick introduction to the course today. As I said, the course webpage is also available on Google Classroom. A link to this is available, and you can also access the course homepage by going to my personal website and going to teaching, and you can get a link over there. So, why study optimization? What is this course all about? Um, Essentially, optimization is important because almost every single engineering problem can be posed as an optimization problem. Right, and it doesn't matter what area you're working on. Almost everything is an optimization problem. For instance, if you want to do chip design, you want to pack the maximum number of transistors into a small enough area. So you want to, let's say, maximize compute within a certain dimensions of the chip. In wireless communication system design, you want to be able to communicate effectively. Say, if you think about, say, cellular communication, you want to ensure that, let's say, your download speed is as large as possible for a given, let's say, power constraint. So whenever you're communicating, your cell phone has a finite battery. You don't want to use too much of your battery, but at the same time, you want to, let's say, upload and download videos at the highest rate possible. Right? You can think of that as an optimization problem. Let's say you want to detect an object in an image, right? You want to make sure that the reliability of detecting a particular object, suppose you are trying to detect people in a given image, you want to ensure that you don't miss people, and at the same time you don't want to overcount. Let's say if there's one person and your algorithm outputs 2, then that's a bad algorithm, right? So so that can be posed as an optimization problem. Let's suppose you want to control a particular plant. Say you have some kind of a motor, and you want to ensure that this motor is operating at a certain rate, depending on whatever you want. You want to ensure that you don't deviate from your desired rate or desired system performance, right? That can also be posed as an optimization problem. Portfolio optimization. So suppose you have a certain amount of money, you want to invest this money over multiple stocks. And of course, if you want to invest, you want to ensure that your returns are as large as possible. So that is also an optimization problem. You want to design an autonomous navigation system. You want to make sure that your car, let's say an autonomous car, follows the prescribed lane and doesn't deviate from it, doesn't cause accidents. Again, you can pose all of these as optimization problems, and in particular we'll see as constrained optimization problems. So effectively, any problem where there's this notion of a best solution or a good solution, effectively any problem where what you desire can be quantified, can be posed as an optimization problem. And typically in most engineering problems, you have constraints and objectives. Right? There's something that you want to maximize or minimize, but you can't do it arbitrarily. You have to follow certain constraints. For example, in wireless communication system design, the constraint could be in the form of a power constraint, or like how large your battery is, right? And for example, the same thing could happen in industrial control. The kind of signals that you can give to control could be limited in a certain way. In portfolio optimization, the amount of money that you have is after all limited. That's a constraint. You don't have an infinite amount of money to invest in stocks, right? And so on and so forth. Right? We'll see a number of concrete examples as to what constraints could be. I'll formulate all of this in a precise mathematical manner, but essentially this course will be about first formulating an engineering problem in terms of a mathematical optimization problem. But mostly this course will be about, suppose you're given a mathematical optimization problem, how do you solve it? how do you decide whether this can be solved efficiently or not? And as we'll see, there's a very broad class of optimization problems. What we'll see are convex optimization problems, which can be solved very efficiently. Right? And that's going to be the focus of this entire course. All right. So typically, what do we have? If you think about an engineering problem, the first step is typically always you're given an engineering problem. The first step is typically to formulate this in some manner as a mathematical optimization problem. But this step in going from the engineering problem and posing it as a mathematical optimization problem may or may not be unique. There could be very different ways of formulating the same engineering problem as a mathematical optimization problem. For instance, suppose that I want to design a communication system, right? Now again, as I said, if you want to formulate it as a mathematical problem, you need some things that could be quantified, correct? So in this case, maybe the parameters that I can control are perhaps how large a battery could be. Now I want to design a cell phone, right? And I want to design a good algorithm that allows me to ensure that I have a large data transfer. My download speeds and upload speeds are as large as possible. So the variables of interest could be the data rate. That's one variable of interest. The second variable of interest could be how large a battery I should have, right? Or how much power consumption does that involve? And the third variable of interest could be, let's say, the latency. I could upload and download files, really large files, but I want to make sure that the amount of latency, as soon as, let's say, I want to download a 1 gigabyte file, it's transferred as soon as possible. Right? So each of these, the first thing is to always identify what parameters can be quantified and what parameters are of interest. Right? So one way of formulating an optimization problem could be, maybe I want to maximize the data rate subject to a certain battery size, or subject to a certain, that the power consumption should be no more than these many milliwatts, right? That's one way of posing it. I could also say I want to minimize the amount of power that is consumed, but the data rate has to be at least, let's say, 1 Mbps. Right? It's the same thing. I want have these competing interests, right? These parameters that I want to be as large or as small as possible. But the same problem could be formulated mathematically in different ways. So there's no single way, there's no one correct way of going about this in many problems of interest. So typically going from the engineering problem to a nice mathematical optimization problem is an art. How you go from here to here is not unique, and it requires you to know something, have some background into this particular engineering problem. You have to know what is it that you want to optimize over and how you want to formulate it. Now once you have a particular mathematical optimization problem, the next step is of course to solve it. And that is also where a little bit of art comes into play. So not all optimization problems can be solved efficiently. It's not good enough if you just formulate a problem. You should also be able to solve it, right? So this, once maybe you designed an appropriate optimization problem, it could be that you could solve this exactly or approximately. Maybe you have a numerical solution to this particular optimization problem. Now, if everything works fine, you can just go ahead and deploy your solution in practice, right? But many a case that is not good enough. Perhaps you test your particular algorithm, and in practice, in the real world, it doesn't work well. then what do? Maybe you need to rework some of your assumptions. Right? After all, whenever you're formulating an optimization problem mathematically, you are making some sort of assumption, assuming that, okay, these are your constraints, this is the objective, and this can be measured perfectly. That may or may not be the case. Okay? So if everything works fine, then good. If not, what do? You go back. You again see if you can reformulate your optimization problem, maybe relax the constraints, maybe change what the objective is, right? And then again go back, see if you can solve this particular optimization problem. Go back and forth, and hopefully you get a solution that is good enough and you can deploy in practice. All right. So that's the general framework. And a lot of this course will basically involve just these two steps. So we'll be given a particular mathematical optimization problem, and we want to know what are the properties of this optimization problem, and given that, how do you solve this? And by the way, feel free to stop me at any point and ask questions. I'd like this class to be as interactive as possible. Right? So firstly, what do you need to know in order to mathematically formulate the problem? So first, you need to identify what quantities are in your control, right? Or what quantities are of interest. And that is typically determined by, so those parameters that are in your control, these are what I will call variables. For instance, the variable could be how much power you can allocate. In the case of, let's say, portfolio optimization, let's take that concrete example. So assume I have a certain amount of money, let's say 1 lakh, and I want to invest this money in across multiple stocks. Right? There are, let's say, 10 different companies that I can invest my money into. So first, I'll have to identify what the variable is. So in this example, could you tell me what the variables or variables could be? Yeah? The companies you choose, well, there are 10 companies, I'm telling you, but can you be a little more precise?
How much money we are going to invest in which company?
Correct. So variable could be how much money am I going to invest in each company, right? There are 10 companies, so I could define 10 variables, one variable which tells me, okay, x1 is going to be the amount of money I'm going to invest into company 1, x2 for company 2, and so on. Those could be the variables. And typically the variables in this course, we'll deal with variables which are either real numbers or they're going to be vectors, maybe n-dimensional vectors. So typically I'll denote vectors in lowercase with an underline. So underline would mean that these are vectors. Lowercase variables, letters are going to indicate real numbers or real variables, and typically uppercase letters will denote matrices. So I'll always assume that the variable of interest is going to lie within some finite dimensional vector space. It's typically just going to be either they're always going to be Euclidean space or something equivalent. So those are my variables. So these are the parameters that I can control. Right. The next thing is to see what is the objective. What is the quantity that I want to maximize or minimize? All right. So let's again think about this problem of portfolio optimization. So I have, let's say I have 1 lakh rupees. What is my objective? Yeah, I want to maximize my profit. But again, we want to be more mathematically precise. How would I pose this as an optimization problem? I'm sorry?
The average yearly return.
Okay, maximize the average yearly returns. What do I need to know for that?
Time. Think over the values that you
Okay.
stocks are performing.
I'm sorry?
How the stocks of the company are performing.
Okay, so these are good ideas. So maybe I could collect data as to how much returns were given by for each company on average using maybe historical data, right? And using that, I could get an estimate, perhaps using some fashion. I get an estimate of what are the expected returns for each company, for each stock. So the objective could be, okay, I want to maximize the expected returns, right? So my objective is going to be some function. I'll call that f0 of x. Okay, in this particular example, maybe stocks, the variable could be x. In this case, in this toy example of portfolio optimization, maybe I have 10 different companies I can invest in. So I could model the variable as a 10-dimensional vector, right? Because each component, so xi is basically the amount of money I'm going to invest into company I. Again, we'll look at a very simple version where I just invest in a particular company. I decide how much to invest in a company at the beginning of the year, and maybe at the end of the year, whatever returns I get, that's what I want to optimize over. In this case, maybe the objective could be perhaps the expected return at the end of year one, end of the year. And maybe I have some estimate, using some historical data, I'm able to estimate how much returns, what is the average return that is given by each company. So in this case, what would the objective function look like? So if I invest 1 rupee into company 1, then maybe I get a return of, maybe the returns is a 20% profit. So if I invest 1 rupee, then I get 1.2 rupees at the end of the year. If I invest 10 rupees, how much would I get? 12. So then how would you express the objective function in terms of the variable? Suppose that, let's say, alpha I is the expected return per rupee for company I. Yep. So basically it would just be alpha 1 times x1 would be the returns that I would get for the from the first company, right? And similarly alpha 2 x2 and so on. Alpha 10 x. Right? So my objective function is essentially this linear function of the variables. Again, we're making some assumptions over here. It's perhaps simplistic model, but it's something that I can precisely formulate. In general, I'm going to have some objective function. Okay, that's the second part. The third part is, well, I can't just do this. I don't have an infinite amount of money. I'll have to think about what my constraints are. Right? So these constraints are going to be generally of the form f1 of x, say less than or equal to b1, f2 of x less than or equal to some amount b2, and so on. Fk of x less than or equal to Vk. Again, if we go back to our portfolio optimization problem, what would be the constraint? The total amount of money I have is, I said, 1 lakh. So my constraint would be that summation I equal to 1 to 10 xi has to be less than or equal to, say, 1 lakh. Right? That's one way of formulating it. But I could have some more constraints. For instance, I know what the expected returns are, but I could sort of try to collect more data. Maybe I collect data and find out what is the risk involved in investing in each company. Because after all, the returns that I get is not fixed, right? I can't say that, okay, I'm definitely going to get 10% returns or 20% returns at the end of the year. There's always some amount of variability. So maybe I collect some more data and find out what is the variance of the returns. Right? Maybe for company 1, it's 10% is the expected returns, but then there could be a deviation of maybe 5%. Company 2 could have an expected returns of 15%, but the deviation could be 10%. So I have all of this. Now maybe I want to minimize the variability that is involved. Right? I could set that as a constraint. Right? I could say that, okay, the expected or the estimated variance or the deviation should be less than or equal to, I don't know, maybe 5%. That's a constraint. That's one way of formulating this, but I could have gone back and formulated this whole thing a completely different way. I could have said that for the same problem, again, my objective is still to get the most amount of returns with the least amount of risk, right? I could say that my objective function could be minimize risk with the constraint that my expected returns is at least 10%. All right. So these are two different optimization problems. These are two different mathematical optimization problems for the same engineering problem that I had initially. So how you pose your engineering problem as a mathematical optimization problem could differ. It's up to you to decide how do you do that. But once you have formulated an optimization problem, once you formulated a mathematical optimization problem, then we can go ahead and talk about whether this has a solution and how do you solve this. Is there one solution? Are there multiple solutions? Right? All of these are questions that we will try to address. Right? Any questions? All right. Great. So let's see another example. And this is a basic problem in a very broad area called optimal transport. So let's consider the following scenario. The one of the classic scenarios is the following. So suppose I'm a huge mining company and I have a number of mines. Maybe I mine for I don't know, iron ore perhaps. Right? So I have a number of mines located in different parts of the country. All right, and each of these produces a certain amount of ore. Okay? Maybe the first mine produces, I don't know, 10 tons per day. The second mine produces 15 tons. The third mine maybe produces 5 tons. Okay? These are located in different parts of the country, suppose, and these mines generate ore which has to be supplied to different steel factories. Right? Again, the factories are my customers, and these could be located in other parts. maybe there are 4 different factories, right? And each of these factories have their own set of demands. Okay, let's assume that, again, it's a toy example. So let's assume that the demands are as follows. Maybe the first factory has a demand of 6 tons per day. The second factory has, let's say, 9 tons per day. The third factory has a demand of 7 tons per day. And the fourth factory has a demand of 11 tons per day. Okay. Yeah. Whatever, I'm just making up some numbers, right? Now, again, the whole objective now is to decide how much ore has to be transported from which factory, from which mine to which factory. After all, there are transportation costs involved, right? If the factory is close to the mine, then there's less cost involved. If the factory is farther away from the mine, then I have to spend more in order to transport ore from one location to another. All right. Is the high level problem clear? Are there any questions? Okay. So maybe I know the cost of transporting ore from one mine to a particular factory. So maybe if I want to transport from mine 3 to factory 3, I have, let's say, whatever, I have alpha 33. So this is the cost per ton of transportation from this mine to this particular factory. Similarly, I know what is the cost involved in transporting from any mine to any factory. Right? So let's assume that. So again, my engineering problem is to transport the ore from the mines to the factories with the least amount of cost. Right? So the engineering problem is minimize transport cost from the mines to the factories. Right? The total transportation cost that is involved. Now, again, I'm talking about mines and factories, but this could be a number of other problems. It could be that I'm generating electricity, I have a number of cities to deliver to, and I want to find out what is the cost that is involved in order to, let's say, lay electrical lines from these power plants to these cities. So a number of different problems can be posed in the same sort of framework. Okay, so that's the cost that is involved. So first I have this engineering problem and I want to pose this as a mathematical optimization problem. So let's think about one particular way of formulating a problem. I know how much ore is being produced by each mine, right? And I know what the particular demands are, right? Let's suppose, let me call, let's say that Pi is the amount of ore produced by the ith mine. And similarly, let's say that Di is the demand by the ith factory. All right. In this case, whatever P1 is 10, P2 is 15, P3 is 5, and D1 is 6, D2 is 9, D3 is 7, and D4 is 11. Yeah, just something. So in this case, let's try to formulate a mathematical optimization problem. What are the variables? The first step is always identify what is in your control. What are the variables that are involved? Yeah, one of you. Okay, so the amount of ore that can be sent from the ith mine to the jth factory. So let's say that xij is the amount of ore that you plan to transport from the ith mine to the jth factory. Okay, fine. So now we have the variables fixed. What is the objective function? What do I want to minimize? Again, as I said, okay, distance traveled could be one thing, but what I'm saying is that the cost increases with how much distance has to be traveled, but also in that distance, how much ore you have to transport. So let's say that you're transporting 1 ton of ore from over 100 kilometers. We'll make a simplifying assumption and say that if you want to transport 2 tons of ore over the same distance, then your costs double. Right? So alpha ij is the cost of transporting ore from mi to fj per ton. Right? So if I transport xi tons from I to j, then the cost that I'll incur is alpha ij times xij. Okay? Again, we'll begin with the simplifying assumption. Okay, so what would be the objective function? Yeah. Okay, great. So summation overall I 1 2 there are m mines, n factories. This is going to be alpha ij times xij. Okay, so that could be my objective function. What else? Is this it? Or do I have any constraints? I'm sorry? Why? No, we don't have any such constraint. Right? Okay, so okay, what are the constraints? I'm sorry? Is that's okay. I'm assuming that you can transport any amount of ore across a pair, assuming you have enough ore. Correct. So how do you model that? Correct. So basically xij is the amount of ore transported from mi to fj, from the ith mine to the jth factory, right? After all, we know the limits on how much ore is being produced by each mine. So what is the total amount in terms of xijs? What is the total amount of ore that is sent from mine I? Right, so amount of ore sent from the ith mine, this is nothing but summation j equal to 1 to n xij, right? And how large can this be? Yep, it has to be less than or equal to pi, because that is the total amount of ore that is being produced by the ith mine. You can't transport more than you produce, right? So this has to be less than or equal to pi for all I. Okay, now is there any other constraint? Yeah, exactly. So you want to make sure that the demands are all fulfilled, right? So the amount received by factory j, this is equal to summation I equal to 1 to m xij. This has to be at least pi dj, right? Now it has to be exactly equal to dj, but that's okay. If you supply more, then it doesn't matter. All right, so this is the objective. So now I have a complete mathematical optimization problem, right? So how would I pose it? So first, the variable is a matrix assuming that there are m mines and n factories. I could frame this as an optimization problem with a matrix variable, or I could just stack all of them together as a single vector. And my problem would be to minimize. Okay, there's one other constraint that we've kind of missed here. It's a subtle point. Yep. So I can't transport negative amount of ore from a particular mine to another factory, right? So each xij should be greater than or equal to 0. That's a constraint. So my optimization problem is the following. So I want to minimize f0 of x, which is summation I equal to 1 to m, summation j equal to 1 to n of alpha ij xij, subject to a bunch of constraints, which are that x is component wise greater than or equal to 0, and summation over all j xij should be less than or equal to pi for I equal to 1, 2, 3 up to m, and summation I equal to 1 to m of xij is greater than or equal to di for greater than or equal to dj for j equal to 1, 2, 3 up to n. So I had this problem of transportation, and I could formulate this as a simple looking optimization problem. Right? Now in this particular case, even in the previous case, if you notice, the objective function as well as the constraints, they're all linear. Right? They're all linear functions of the variable. So this is an example of what is called a linear program, where the objective function as well as all of the constraints, they are linear. All right. So, okay, we started out with an engineering problem. I framed this as this mathematical optimization problem. The next question that we should ask ourselves is, does this have a solution? Just because I have a mathematical problem doesn't mean that it necessarily has a solution. There may be no way of, for example, there could be no way of satisfying all of the demands. For instance, if some of the DJs are too large and the PIs are small enough, then this may not have a solution at all because you can't satisfy all of the constraints. The first question is there a solution? Second question is, okay, maybe there is a solution. How do we find the solution? And how do we find it efficiently? Now this, as I drew it over here, there are 3 mines and 4 factories. But in practice, in reality, you will come up with optimization problems where the number of parameters, the number of variables that are involved could range in the thousands or even millions. Right? So in that case, you can't really rely on closed form expressions. There's no hope of getting any closed form solution at all. So you could try to numerically solve it, but you should also be able to do it efficiently. If I have, let's say, 10,000 parameters or a million parameters, I should be able to solve for it in reasonable amount of time. I should be able to get a solution in a reasonable amount of time. Right? And as it turns out, there are very efficient algorithms that allow you to solve linear programs. Okay? Not all optimization problems can be solved efficiently. And as we'll see in this course, there's a broad class of problems. If the objective function as well as the constraints are all convex, then it turns out that you can solve these optimization problems efficiently. There's a numerical procedure that allows you to get at least close to the solution or close to the optimum in a reasonable amount of time. That is why the interest of this course is convex optimization and not general optimization. All right. Any questions? All right. So let's see another example. Right. So this time we won't start with an engineering problem, but we'll start with an optimization problem directly off the bat. But first, let's look at the following. Suppose I give you a system of linear equations. Right. Let's say I have ax equal to b. Right. So this a is, let's say, an m by n matrix. X is in Rn and b is in Rn. When does this have a solution? Okay, very good. So this has a solution if and only if B lies within the column space of A, right? But now suppose that B does not lie in the column space of A, right? Let's assume for simplicity that A is a full rank matrix. Actually, disregard that. So in general, suppose that I give you a system of equations where B does not lie within the column space of A. What is the next best thing that we can do? Yep. So let's forget the projection bit a little, because again, it depends on how you formulate your optimization problem, right? So what I want to do is be able to solve this system approximately, right? So if B lies within the column space of A, then we know there is a solution. We don't need to worry anymore. Now suppose that B, the vector B, does not lie within the column space of A. I want to choose an X such that AX is close to B, right? I can't find an exact solution because an exact solution does not exist. So I want to find an approximate solution. All right. First, so right now I know what the variables are. My variable is this vector X. But right now I should define what my objective function is. And there are a number of ways of defining the objective function. Correct? So typically what you've seen in least squares is the case where the objective function is the L2 norm or the L2 norm squared of the error AX minus B. Right? The L2 norm of AX minus B the whole square. That could be my objective function. If I use this objective function, then I get one particular solution. In this case, again, AX is close to B in some sense, in the L2 norm sense. But equivalently, I could also ask for a different norm, right? I could have said that I want the one norm of AX minus B to be small. Again, that also gives me an approximate solution, but the solution I get would be different from the case where my objective function is the L2 norm squared of AX minus B. Right? Now, assuming that this is my objective function, AX minus B the whole square, what is the solution that you've seen in your linear algebra course? Yes, suppose I wanted to minimize AX minus B the whole square, L2 norm of AX minus B the whole square. Okay, so someone said it's A, what is it? A transpose A the whole inverse, A transpose B. How do you know that A transpose A is invertible? Sorry? A transpose A is a square matrix, I agree, but does it have to be invertible? Divide what? No, I'm saying that A transpose A need not be full rank, right? Then A transpose A need not be invertible. What do you do there? Okay, what is the pseudo inverse? So really what you do is you look at the system of linear equations A transpose AX equal to A transpose B. I claim that this has a solution irrespective of whether A transpose A is invertible or not. Right? And this is a system of linear equations that you can solve using whatever your favorite method, Gaussian elimination. Right? This does not require A transpose A to be invertible. Right? If A is full rank, then this is your solution. This is the least square solution. Right? If not, then the least square solution is obtained by solving this system of linear equations. But
full rank or the lesser dimension?
Whatever, it's full rank. But when I say full rank, I mean that the rank is equal to the number of columns in this case.
Yeah, otherwise it would be a square meter.
Yeah. Okay. So now I brought this example up for a reason. We'll try to see what are the features of this particular optimization problem. In this case, it was an optimization problem where the variable was an n-dimensional vector, and I didn't have any constraints. Right? And what kind of an objective function is this? Yep, correct. It's a length square. It's basically a quadratic. Right? So this is an example of a quadratic program. And it's also an example of an unconstrained optimization problem. There are no constraints in this case. But this is a nice simple example where I can obtain a closed form solution. Right? Because I know how to solve this exactly. All I have to do is, if A is full rank, then I have this nice formula to compute the solution. And if not, all I have to do is apply Gaussian elimination to this system of linear equations and get the solution. In practice, this is not the case. For most problems that we see, we won't be able to get such nice closed form solutions. All right. And also, you have to think about, let's look at the following alternate problem. Recall that our objective function was to minimize the sum of squares, or the L2 norm squared of the error. Suppose instead that I wanted to minimize the L1 norm. Right? What are the features about the L1 norm that are not as nice as the L2 norm squared? Yep, so one big thing that we'll see is that the L1 norm is not differentiable. And we'll see that some nice optimization algorithms don't work when your objective function is non-differentiable. So in practice, what you would like to have is an optimization problem where the functions are nice and smooth. But later on, we'll see that even if the function is non-smooth, you can still modify those algorithms as long as these functions satisfy certain properties. You can modify them to behave as though they are smooth. You can still use the optimization, the algorithm that you used for smooth functions. With a little bit of adaptation, you can also make it work for non-smooth functions. All right. Okay, any questions? Okay, so in many of such problems, there's a sense of um, you have some intuition as to how your objective function or your constraints behave. For example, in this previous problem of optimal transport or portfolio optimization, your objective function and the constraints were linear functions, right? And we have some sense of some geometric intuition as to how they behave, right? So a linear function in in let's say R2 is just a line, right? Similarly, in R3, a linear function could either be a line or it could be a plane, right? And likewise, linearity in R3 or R4, these are all going to be hyperplanes. So these are all nice structures which at least we get some intuitive sense of. When I say that the function is quadratic, I do have a rough sense of what it means to be quadratic. Looks like x square, some sort of a bowl shaped function. But in this course, we want to go beyond that, beyond spaces where intuition helps us, but also to spaces where we don't have too much of an intuition. So let's see one concrete example of that. So I won't give too much details, but I'll just formulate what the optimization problem is and not give you the background of where it comes from. So I'll pose an abstract mathematical optimization problem. The problem is as follows. The goal is to find, again, I'll have to define what the variable is. My variable is going to be a matrix, right? It's going to be a square matrix, and in fact a symmetric matrix. Okay. So if I think of a symmetric matrix, how many independent variables does a symmetric matrix have? So I have an n by n symmetric matrix. How many independent variables are there? Yeah, n into n plus 1 by 2, right? I'm sorry? Correct. So in the first, let's assume that we're only counting. So the independent variables are all of the variables along the diagonal and maybe above the diagonal, right? So in the first column, because below the diagonal, everything is just a reflection of what's there above the diagonal. So how many independent variables in the first column? 1. Second column, 2. Third column, 3. So the total number of independent variables is 1 plus 2 plus 3 plus 4 up to n, which is n into n. So that's my variable. Again, effectively I could pose this in terms of only the independent variables, but there's a specific reason why I'll define the variable to be a symmetric matrix. Okay. So this is my variable. My objective function is going to be the following. This is going to be the logarithm of the determinant of the following matrix I plus h x h transpose, where this matrix H is an arbitrary m by n matrix. I'm sorry. Again, I'm not going to go into too much of the background of where this objective function comes from. Effectively, maybe just to give a very high level overview, this turns out to be the maximum rate, transmission rate that you can achieve in a wireless communication medium with M with N transmit antennas. So if you think of a wireless communication channel where the sender has N antennas and the receiver has M antennas, and H is in some sense the attenuation between each pair of antennas, then this turns out to be the maximum transmission rate that you can achieve over this particular channel. So let's not get into where this came from, but believe me when I say that this is an objective function which is of practical interest in wireless communication. If you've taken a wireless communication course, then you may have seen this particular quantity as the capacity of a wireless channel, right? Yeah, the goal is to maximize this particular quantity. Right? But again, it's not to maximize this over arbitrary symmetric matrices. I have a constraint, and the constraint is that X should be positive semi-definite. Okay, we look at positive semi-definite matrices in more detail in the course, but one simple way of thinking about what a positive semi-definite matrix is, it's a matrix where all of the eigenvalues are non-negative. Right? So I want to maximize this objective function, which is complicated looking as it is. It's log of the determinant of some matrix, and I want to maximize this over all possible symmetric matrices X having non-negative eigenvalues. Right? And I'm saying that the same set of tools that can be used to solve other optimization problems, Euclidean optimization problems, can also be used to solve this particular problem. Right? In this case, again, we're dealing with matrices, symmetric matrices, and positive semi-definite matrices, for which we don't have so much of a geometric intuition. Right? If I give you a particular set, let's say I give you Euclidean space and let's say a sphere in Euclidean space, right, or a ball in Euclidean space, you have an intuitive feeling of what that looks like, right? Or I tell you that the constraint is the set of all vectors that lie within a polyhedron. Again, you intuitively have a picture of what that looks like. You think of a cube or some weird polyhedron, you get some intuition. But now I'm telling you that X has to be positive semi-definite. I don't have intuition for this particular. I don't know what it looks like geometrically. So I want to develop mathematical tools that allow me to analyze even optimization problems of this particular form, where I don't have intuition to what the problem looks like, what the geometry looks like. And we'll see later on in the course that this set of all positive semi-definite matrices, that is a convex set. Again, I've not defined what convexity is yet, but it's a convex set, and it has certain geometric features that we can identify with some other geometric features that we have in Euclidean spaces. We'll see later, this set of positive semi-definite matrices behaves like a cone. We have an intuitive idea of what a cone looks like, right? There's a point, it's pointed at one end and it's spreading out outwards. Right? It turns out that the set of positive semi-definite matrices has many mathematical features of cones, and we can use that to design algorithms to solve such optimization problems. All right. Any questions? Okay. So first, I'll introduce sort of a canonical or a standard form for the kind of optimization problems that we look at in this course, right? So I'll call this standard because many optimization problems can be reduced to this particular form. We'll see that right away. All right, so the standard form will be the following. The standard form is always to minimize some function f0 of x subject to constraints f1 of x less than or equal to b1, f2 of x less than or equal to b2, fm of x less than or equal to bm. So there will be m constraints and a single objective function, and it's always going to be minimized. So everything in this is important. So first you want to minimize the objective function, and each of these constraints are inequality constraints. It's less than or equal to, and it's always less than or equal to, not greater than or equal to. Any questions? Okay, so let's first see what kind of optimization problems can be brought to this standard form. Suppose I give you an optimization problem of the following: max of, let's say, x square subject to x, let's say x1 square plus x2 square subject to x1 plus x2 greater than or equal to 2. Some optimization problem. Maybe also x1 minus x2 less than or equal to 1. Can you bring this optimization problem to standard form, to this particular form? Yeah, which one? Okay, so basically if I have a maximization problem, so maximizing a function is the same as minimizing the negative of that particular function, right? So if you want x1 square plus x2 square to be large, then it's the same as asking for minus x1 square minus x2 square to be small. So this is equivalent to minimizing x1 square plus x2 square subject to, is the first constraint in the standard form? It is not. So what do I do to bring it to standard form? Yep, you bring this to the right hand side and this to the left hand side. You just take the negative. Minus x1 minus x2 being less than or equal to minus 2, and x1 minus x2 less than or equal to 1. So as long as I have a maximization problem, I can bring it down to a minimization problem just by taking the negative. It's not the only way, mind you. I could instead also take any decreasing function of this, right? So for example, I could say that this is also the same as minimizing, I'm sorry, I made a mistake over here. There should have been a negative sign. right? But instead of doing this, I could also have said I want to minimize e to the power minus x1 square minus x2 square. Because minimizing e to the minus x1 square minus x2 square is the same as maximizing x1 square plus x2 square. So I can always play these tricks. Similarly, suppose I want to minimize the L2 norm of x. It's the same as minimizing the L2 norm squared of x. Right? So both of them will have the same solution. But sometimes certain formulations are better than others. Which one? Fine. Could formulate them as two different inequality constraints, but again, yeah, at later point I'll need another thing. So I'll also allow c times x equal to d. All right, so I'll also have, in general, I could also have fi of m plus 1 of x. I think that was the notation I used. So h1 of x equal to let's say c1, h2 of x equal to c2, and so on. Right? So I'll allow equality constraints as well. Again, I could define an equality constraint using two different inequality constraints, but I'll separate that out for a specific reason we'll use much later on in the course. I was going to raise that particular point. So now suppose I have the same problem. Let's say max of, let's say, x square subject to x less than 1 and x greater than minus 1. Okay, there's another problem. Can this be brought to the standard form? So x is real, right? Yeah. Okay, the objective function can be transformed to the standard form. Instead of looking at max of x square, it is the same as min of minus x square. Not a problem. But what about this strict inequality constraint? Can you express strict inequality constraints using these inequality constraints? How many say yes? How many say no? You can't. The others? Okay, so people who say that you can give inequality constraints, can you give me a set of inequality constraints for which? Okay, what would be that constraint on K? Okay, so there's a suggestion which is, let's just look at the constraints, okay, not worry about the objective function for now. Let's take one inequality constraint which is x less than 1. Okay, can I formulate this? So this basically defines a set, right? Set of all x for which x is less than 1, strictly less than 1. Can I formulate this in terms of inequality constraints? So one solution was, I think x plus, you say that x plus epsilon is less than or equal to 1. Is that correct? Is that what you were suggesting? So what would be the constraint on epsilon? What do you mean? There's only one variable x, right? Epsilon should be between 0 and is this, am I reading this correctly? Would these constraints give you the same as this?
X plus epsilon equal to 1?
I'm sorry?
It's not the x plus epsilon equal to 1?
Which one? Yeah, I'm asking you how it can be formulated. It's totally up to you. Do you want to say x plus epsilon equal to 1 or less than or equal to 1? Okay, equal to 1, let's say. Are these two the same? Are these two sets of constraints the same? How many say yes? These two sets of constraints are the same. How many say they're different? The rest of you have to decide one way or another. So what is the problem here? Why are these two not the same? Correct. So in this case, x equal to 1 does not satisfy the constraint. Right? But on the right hand side, I can find an epsilon for which x equal to 1 satisfies the constraint. I can just set epsilon equal to 0 and x equal to 1. That would still satisfy all of these constraints. Correct? The only way where I could force x equal to 1 to not satisfy the constraint would be to enforce that epsilon be strictly greater than 0. But I end up with the same problem. Right?
Okay, now around 0, we define something like, okay, put 0 defined equals epsilon only, but then something like 1 by epsilon should be defined as that you would get rid of 3 then 0.
But one by epsilon should be defined. That's a problem, right? That's a weird constraint that you're imposing. It's still not in the standard form, right? My standard form has to always have these kinds of constraints. So they are different, right? So this problem cannot be brought down to the standard form, right? And there is a subtle reason as to why I'm only going to look at problems of this particular form. And you can say what the reason is just by looking at this particular problem itself. What is the solution to this problem? Is there a solution to this particular problem?
If you don't put an equality on the constraints, there's no exact solution.
Yep. Yes. So therefore, the maximum is not defined. You see, the supremum is defined, but the maximum is not defined. As we'll see later, one of the reasons is that this set, the set of constraints, or the set that these constraints define, is an open set. It is not a closed set. On the other hand, we'll only be interested in constraints that define closed sets and which guarantees that a solution will exist. Either there'll be no solution which satisfies the constraints. If the constraints are satisfied, then you will be guaranteed of a solution. Right? So that's again a subtle point. We'll see more of that as we go on. Right? Any questions? Right. So this class of problems that we look at is in some sense restrictive. It's not, you can't pose any arbitrary optimization problem in this particular form. Firstly, there's only one objective function. That's something to keep in mind. Only one objective function, and you have multiple constraints, any number of constraints, but all of them have to take this particular form. But as long as it takes this particular form, I'll tell you what we can do with this. Right? So it'll be up to you to bring it down to this particular form. If you can, then we'll see that we can design solutions around this. At this point, no. For a good chunk of the course, yes, we will impose certain constraints, but some part of the theory that we'll develop will not, it won't matter what the F1, F2 and so on are. Any other questions? Yeah. Correct. Why? Okay, if it is closed, why you have a solution? I'll come back to that a little later. We need a little bit of real analysis to see why that is the case. I'll promise I'll get back to that, but it'll be at a slightly later point. There's a result, again, I won't prove it, but there's a result in real analysis which says that as long as you have a set that is closed and bounded, yeah, exactly, a limit point will exist, and therefore a solution will always exist. Either a maximum or a minimum will always exist. That is basically what we will use. Of course, this is not enough, but there's another reason why we look at only this set of constraints. Any other questions? I'm sorry? I'm not going to take any manual attendance. ERP, it's not working, is it? Okay, I'll raise a complaint with the ERP, and then hopefully by next class I will be resolved.